First of all, I would like to thank you all for your virtual presence. Well, it's nice to be here with you in this virtual meeting. So, as you know, we are here for the oral session number 5, room A, and our topic will be wireless and network communications. Well, I am the chair of this session. My name is Slimane Benmahmoud. I will be assisting you to present your research work during this session. Well, here are just some guidelines and orientations. Please make sure to turn off your camera and don't turn it on. So everyone will have like 15 minutes to present his work. Please follow carefully other attendees' presentations. If you have any question, you may use the chat room. When it is your turn to present your work, you will be given the option to share your presentation and to talk. So please accept sharing your screen when you are asked to do so, and make sure just to share the application that you are using, either if it is a PowerPoint or a PDF one. So all participants are here. So let's start with the first talk that will be given by this one, yeah. Okay, try to do this.
Here, normal mode, maybe close.
No, don't close it. If you close it, you will be out of the session. Try to put it outside, just outside, or to reduce its size so we can see the screen.
No, I will maybe resize it. No.
Yeah, try to do so.
No, it's the minimum size.
Just put it in a given place and start your presentation. Please go ahead, Mr. Gouthi.
Thank you, Mr. Slimane. So, بسم الله الرحمن الرحيم. صلاة والسلام على أشرف المرسلين. My name is Abdullah Gouthi. I'm a lecturer at École Supérieure des Sciences Appliquées de Tlemcen. Also, I'm member in Telecommunication Laboratory of Tlemcen, as my colleague Ms. Bekay. And I'm very happy to present for you our work titled The Novel Model Using Radio for IoT Self-Configuration System. So, for this presentation, we have the following plan, starting by an introduction. After that, we will present the self-configuration, and we will see what is it by presenting some cases of self-configuration. And the third point we will present, in the third point we will present our contribution based on a component approach. After that we will present and discuss our obtained results, and a conclusion with computer works as the last point. So the IoT system are one of the largest networks in the world. They contain a large number of devices such as phone, car, TV, airplane, whatever you want. And the quality of the system is measured by several factors such as self-maintenance, auto-update, and self-adaptation. But with this huge number of devices, develops many problems. I think the most certain are how to install and of these devices. The second question is how to explore all these devices. And we have another problem to solve, is that the proposed solution must be automatic. It means with the minimum of human interaction, of course, in real time, in runtime, and also that it must accept an open space of configuration. For this, as a solution to these problems, we propose a self-configuration of each new IoT device into the system. So the question is now, what is the self-configuration? By definition, self-configuration is the ability to a system to allow modification of subset of the system during its execution without interruption of service. In the next slide, we will present three processes for the self-configuration to better understand what the self-configuration is. So the first one is the primary backup system. In this case, the self-configuration is the transition between source S and the target S prime configuration through the following steps. So the first step is to persist information about S prime on stable storage of a column of S. After that, we will have to deactivate S. After we identify and transfer all committed S to S prime, persisting it on storage table. And in the last steps, we activate S prime. The second system is for the reuse module unit. This configuration process is to reuse some embedded system resources or add embedded hardware device or add function to the middleware. And the steps are analyzing the embedded system resources, dynamically loading them to the middleware, and the last step is resisting them to on the middleware. And the last one is for the self-configuration of the component software approach. And in this case, the self-configuration can be done by the following steps. The first step is to identify and delineate the part of the system to be reconfigured, system execution, change the configuration of the system by adding or removing some parts. After that, we have to transfer the reports to the new parts, and in the last steps, resume execution of interrupted portion of the system. These three systems seem to be different. However, their abstraction is that they target the same things, which means reconfiguration, even with their different unit of composition in the nature, but they share the same properties such as elemental, independent, connectable, and maintainable. So these four properties for us are the main criteria to choose the focal elements for our model. For this reason, we choose the components. Okay, we will choose the components model as the smallest unit for configuration model. So, by definition, a component is a non-trivial, merely independent and replaceable part of system that fulfills a clear function in the context of well-defined architecture. And the architecture of the component is characterized by a black box in the middle, which contains the process, and a set of interfaces such as control interfaces, inputs, outputs interfaces, and other interfaces for configuration and properties of the components. This architecture gives us, or gives to the components, a set of characteristics such as encapsulation, composability, description, reuse and evolution, generic components model, adaptation, and in the last, configuration. With this characteristic, the set configuration can be by connecting with the two components. It may create a link between input-output interfaces, or disconnect two components by deleting the link, of course. But in some case, the two components or the interfaces of the two components are incompatible. So we need to add another kind of component, which we will call adapter, and to connect them. And the self-configuration can be possible by the following actions. The first action is to connect directly the two components, or connect two components via an adapter, disconnect the two components, create an adapter, destroy the adapter. So after analysis of all these actions and the characteristics of components, we can propose the following model, or a meta model for the self-configuration. And this model represents an abstraction of any of the composition of any system. According to our model, the configuration class is defined by a composition of set of final components, adapters, and links. Note that each final component adapters are an implementation of interface called components. Noting that this last one, components interface, is a composition of two classes, interface out and interface in, which implements the same interface called interface, of course. And with this meta model, any developers can instantiate a model for him system. Okay, so under the configuration can be seen as a set of rules used to coordinate between different elements of the system and to handle the system state changes. So the first rule is to add a new component to the configuration. Knowing that the gray object here is an existing object and the green ones are the new object. So we can understand now that with this rule, add components rule, we can add a new component to an existing configuration, including interface in and interface out. Also, we can delete the components, including the interfaces, with delete components rule. There is another rule for to create a link and add this link to the configuration by linking the input-output interfaces of two existing components. As the case of components, we can also delete the link and remove it from the configuration. And there is another rule. We create another rule for to create an adapter and putting it in the configuration and linking to incompatible existing components. And the last rule, of course, is for delete this adapter. So by applying these rules, we can get a graph, state transition graph. Here we have the green state, or the state 0, is the start state with 0 components inside. By applying the add components rule, we get a new state, state number 1. In this case, we can go to the state number, we can come back, okay, we can come back to the state number 0 by applying delete components. Or we can go to the state number 2 by applying add components rules. Here, in the state number 2, we get a configuration with the 2 components. So in this case, we have a new kind of rules that we can apply, such as add links and add adapters, because with the 2 components, we can create a link and we can create an adapter between them. So notice that here, the gray states, okay, like such as 1, 2, 3, 6, and 8, it means that this state has achieved all its possible transitions. For example, in the state number 2, all possible transitions are delete components to come back to the state number 1, or added components to go to the state number 3, or we can apply add adapter to go to the state number 5, or in the last case, add the link to get state number 4. In another hand here, the state number 4 in blue color, such as 7, 5, 14, etc., it means that this state can produce other states by applying the new configuration rule. So this is make our graph here in an open space, and we can develop an infinite number of states. In the last, as a conclusion, our self-configuration model offers to the IoT system an infinite number of configuration, flexibility, and better adaptation to the different environmental change, and it it allows us to increase the system performance. But to get this work more efficient and as a future task, we want to model events as trigger for self-configuration rule and model constraints as a condition for activating self-configuration rule. Thank you for your attention, and any question, please?
Well, thank you so much, Mr. Houthi Abdellawi, for this clear and deeply explained presentation. So,
Welcome.
yeah, so from your presentation, we can understand that you have developed a new RIO-based model for Internet of Things self-configuration systems.
Yeah.
Well, my first advice to you is if you are thinking of extending your paper and like you want to publish it, is to change your title to be more meaningful as follows. You can make it like this: a new RIO-based model for a self-configurable Internet of Things system. You see what I am saying? I can send you. Yeah. Anyway, I can send.
Yeah. Thank you.
Yeah, I can send you this by private message or by email if you want. Well, my first question is this.
Thank you. Yes.
You are welcome, sir. My first question is this. Could you please explain to us what does this RIO stand for? Because sometimes you call it a coordination language in subsection B of section 3, and sometimes you call it a tool in the discussion section. So could you please tell us a bit about it?
Yeah, RIO is some mathematical model developed to modelize configuration of systems. Is an abstraction for some systems, and we can simulate and see what's the behavior of the system in the time. Okay, exactly. There is no time when we talk about actions, okay, or rules. Okay, so RIO use these rules to make configuration and coordination between the different parts of in the system, because it's a high level of abstraction. So for us, the system is a set of objects. Okay, and each object for us is a black box which have some process. We don't know exactly, but we take it like a black box with the input-output data. So RIO helps us to simulate and to modelize this system with our vision. For example, for us, the vision that we try to improve with RIO is the self-configuration. How can a system change the behavior or take into the account any IoT device, new IoT device? I think, okay?
Okay, it's clear now. Another advice is that in the abstract of your paper, it is not clear what are you proposing exactly. So my advice to you is to reformulate it so it make it and you can make it more clear what are you proposing exactly. That's all what I have for you, Mr. Houthi Abdellawi, and thank you again for your presence and for your presentation.
Welcome. Thank you too for sharing this presentation. Thank you.
Okay, you're welcome, sir. So let's go to the next one. The next presenter is Miss or Mrs. Sophia Shergi. She will be presenting her paper with the title Design and Realization of a Visible Light Communication System for Wi-Fi Application. So I'm going to give her the option to share her screen. Okay.
Assalamu alaikum.
Alaikum salam. Please go ahead. Your presentation is displayed on all the screens of the participants. So please go ahead and start your presentation.
You can see my presentation?
Yeah, it's displayed on all the screens of the participants. Just go ahead and start, please.
You can start. I can start.
Yeah, you can start.
Yeah. Okay. Assalamu alaikum. My name is Sherry Sofia. I am a student. I do this work in the University of Biskra with Mr. Abdel Salim. My presentation is about the design and realization of a visible light communication system for Wi-Fi application. So it's the presentation plan. The first thing we'll say the introduction. Secondly, we'll see the VLC system. And after that, we'll say the conception and the realization of a VLC system. After that, we'll say the transmission results. And finally, the conclusion. Introduction. Alors, avec l'émergence des nouvelles technologies comme l'Internet des objets, on a un problème qui se pose, un problème qu'on appelle le crunch spectral, spectrum crunch. It's the saturation of the radio frequency band. Donc ça fait with the increasing number of devices, la bande des radiofréquences est limitée. Il ne peut pas prendre en charge ce nombre constant ce nombre croissant d'appareils mobiles. Donc, comme solution, on propose d'utiliser un autre spectre, qui est au lieu d'utiliser le spectre des radiofréquences, on va utiliser un autre spectre, qui est le spectre des Visible Light Communication, le spectre visible. Le spectre visible, comme on peut le voir, s'étend entre 430 THz, des fréquences entre 430 THz et 790. À savoir, there are difference between the optical wireless communication and the visible light communication. The visible light communication is just that's one, this part of the spectrum, but the optical wireless communication include the infrared, the visible, and the ultraviolet communication. On propose d'utiliser le visible light communication parce que c'est la technologie qui peut être utilisée pour la communication et également pour s'éclairer, alors que l'optical wireless communication, non. So we'll begin with the VLC system. First we will see what's the VLC. VLC, the Visible Light Communication, c'est une technologie qui utilise les communications optiques, c'est-à-dire qu'on va utiliser les LED, plus précisément, pour envoyer une donnée. La LED va clignoter assez rapidement, ce qui va créer une fréquence. C'est cette fréquence qui va être utilisée pour envoyer des informations. Ce clignotement est assez rapide, donc il est non perceptible par l'œil humain. Et qu'est-ce que le Wi-Fi? Le Wi-Fi, is the term used to Wi-Fi is the term used to refer to the fast, cheap wireless VLC communication system, which is the optical versions of Wi-Fi. Donc c'est la version optique du Wi-Fi, le Wi-Fi. Alors on peut voir le VLC System Architecture. Donc on peut voir que on a un émetteur, l'émetteur va traduire l'information électrique et va l'envoyer en tant qu'information optique grâce aux LED. C'est les LED qui vont envoyer l'information. Au niveau du récepteur, c'est le photodétecteur qui va recevoir cette information et il va faire l'inverse que l'émetteur. Il va convertir cette information optique en une information électrique qui va pouvoir être lue par le terminal. Alors, maintenant, on va passer à la partie pratique, the conception and the realization of VLC system. Alors, this is the synoptic diagram, c'est en général ce qu'on a fait. Donc, on aura un terminal soit un PC, soit un mobile, qui va envoyer son information. Cette information va être traduite grâce à un Arduino Uno et va être envoyée à la LED. La LED va envoyer l'information qui va être détectée par le photodétecteur. Il va faire l'inverse, va traduire l'information optique en une information électrique et le terminal va pouvoir recevoir cette information. Le terminal peut être un PC ou un téléphone portable, par exemple. Alors, d'abord, qu'est-ce que l'Arduino? L'Arduino is an open source electronic prototype platform. C'est un microcontrôleur de la famille des AVR, Atmega 328. Alors, voici l'expérience qu'on a pu faire en laboratoire. Donc, on a utilisé une LED. Les LED, c'est un duplex communication system, c'est-à-dire qu'un terminal peut envoyer et recevoir en même temps. Donc, grâce à l'Arduino, l'utilisateur va taper son texte ou l'information envoyée. L'information va pouvoir être convertie en signal électrique et puis en signal optique et va être envoyée grâce à la LED. Les LED qu'on a utilisées, c'est des 12 volts LED, comme on peut le voir. Ensuite, au niveau de la réception, si par exemple le terminal a une information à recevoir, il va la recevoir grâce à un photodétecteur. Le photodétecteur qu'on a utilisé, c'est un phototransistor. Il y a plusieurs types de photodétecteurs. En l'occurrence, on a pu utiliser un phototransistor BPW40. Ce photodétecteur va traduire l'information et va la rendre lisible grâce à plusieurs composants électroniques et être transmis grâce à l'Arduino. L'Arduino va pouvoir afficher le message ou l'information. This is the organization chart of transmission and reception. Alors, c'est ce qui se passe au niveau de l'Arduino. Donc, au niveau de l'Arduino, quand on tape un texte ou une information, le texte va être lu, ensuite va être converti en code en binaire, comme tous les systèmes électroniques, va être envoyé de serial port et va être envoyé à la LED via une modulation. La modulation qui est utilisée, c'est la modulation OOK, partout ou par rien. Ça veut dire que c'est un ensemble de bits de 0 et 1. Le 0, ça sera 0 volts, et le 5, et le 1, ça sera 5 volts. Ça va s'allumer, c'est simple. Et au niveau de la réception, c'est le photodétecteur qui va recevoir l'information, qui va faire l'opération inverse que la réception. Il va convertir ce signal optique en signal électronique qui va être converti en texte, le code ASCII en texte, et va être affiché au niveau du moniteur. Alors, on a pu faire ça, c'est de la programmation sur Arduino, donc en langage C. Ensuite, on a pu voir les résultats, donc on a pu envoyer un message. Par exemple, ici, the communication visualization, I send hello, it's a demonstration about my Li-Fi project. Au niveau de l'animation, et donc on l'a très bien réceptionné. On peut voir aussi via l'oscilloscope le signal d'émission et de réception. Ils sont à peu près identiques, ce qui nous a permis une bonne communication. Alors c'était les débuts de l'expérience. Donc après on a pu sécuriser la transmission. With the algorithm AES. AES, c'est Symmetric Baroque Cipher Algorithm. Donc symétrique cryptographie, ça veut dire que la même clé est utilisée for encryption and the same is used for decryption. On a plusieurs types de block encryption algorithmes. On en a par exemple, on a le 128, le 192 ou le 256 qui utilisent une clé de même taille respectivement. Donc ça c'est l'organigramme de comment ça se passe avec l'AES. Operating mode CBC. Alors le mode CBC, c'est un mode d'opération. Ça veut dire c'est une manière de traiter les blocs de texte au sein d'un algorithme de chiffrement. Donc en l'occurrence au sein de l'algorithme AES. Alors ça c'est l'organigramme général. Donc le block cipher encryption ici, c'est la AES qu'on a vu précédemment, et c'est le plaintext. Le plaintext, c'est le message qu'on va insérer. Le IV, c'est un initialization pixel qu'on va introduire d'une manière manuellement via notre ordinateur. L'utilisateur, oui, c'est l'utilisateur qui va l'introduire. Alors le padding, donc comme l'AES va utiliser, comme on a vu précédemment, il va utiliser des tailles fixes, on a dit 128, etc. Donc on a un problème, si par exemple notre texte est de 5 bits, par exemple on a besoin de plus d'une taille fixe, on va rajouter ce qu'on appelle le padding, bourrage. Ça veut dire qu'on va rajouter des bits à la valeur pour avoir une valeur appropriée. Donc, par exemple, si on a un manque de 5 bits, on va rajouter 5 bits d'une valeur de 5. Si on a 4 bits manquants, on va rajouter 4 bits d'une valeur de 4, etc. Ce type de padding is named Public Key Cryptography Standard, PKCS7. Donc, au niveau de notre réception, on a pu voir les résultats. Donc on a des résultats for implementation of AES-CBC encryption. Donc, voici le texte qu'on veut envoyer. Avec 100 bits de bourrage, c'est le texte, c'est lui-même. Avec les bits de bourrage with padding, on va rajouter ces bits de padding, ces bits de bourrage qui ont été insérés. Donc, et ça, c'est le texte cipher. C'est ce cipher qui va être envoyé. Comme ça, si personne n'a la clé pour decryption, donc ils ne pourront pas lire ce message. Et au niveau de la réception, on va insérer parallèlement des clés pour pouvoir lire le message. Et donc, on va détecter le cipher et on va pouvoir le traduire, le convertir, le rendre, pouvoir faire la decryption. Voilà. Donc, bien sûr, on a envoyé l'information avec le VSC Communication. Ensuite, après avoir fait une encryption, after encryption and decryption, we use the Base64 Coding. C'est un codage qui permet de réduire la taille des données et pour assurer une bonne transmission des données sans erreur. Donc, on a envoyé notre texte. Bon, alors, donc on a testé avant de faire donc on a testé ici. Par exemple, on a envoyé le texte, on a fait un codage, on a utilisé encryption. Et au niveau de la réception, on a fait le decoding. On a pu recevoir le même message qui a été envoyé avant. Alors voici les résultats. Alors bon, après qu'on a testé le coding, on peut maintenant faire le encryption and coding, and decoding and decryption. Ça veut dire que l'émetteur va utiliser encryption and coding mode, et au niveau de la réception, il va faire decoding and decryption mode. Et donc toutes ces techniques, c'est pour protéger la donnée. Donc on a pu récupérer le message initial. Voici les résultats de la transmission results. Donc après, on a pu tester cette transmission via différentes distances. La distance maximum qu'on a pu avoir était de 2 mètres. C'était une transmission sans erreur, bien sûr. Et on a également pu changer la rapidité de la modulation. C'est-à-dire que plus il est rapide, plus le clignotement de la LED va être rapide et plus il va être non perceptible par l'œil. Donc voici. On a pu remarquer qu'avec le phototransistor qu'on a utilisé, il n'est pas très adapté aux longues distances. Plus la distance augmente, plus la rapidité doit être moins élevée. For conclusion, we can say the use of visible light communication est une bonne alternative au problème de trace spectrale. On a pu assurer une bonne communication de plus de 2 mètres, une communication sécurisée. Alors déjà, on a sécurisé notre communication, plus on a atteint 2 mètres. C'est quelque chose qui n'a pas été atteint auprès des travaux ultérieurs avec l'utilisation de l'Arduino Uno. Donc on peut dire que l'IFI technologie, pour résumer, on peut dire que l'IFI technologie peut être un bon complémentaire au problème de radiofréquence. Thank you.
Well, thank you, Ms. Sophia Shergi, for your presentation. Well, let me check the chat room if there is any questions. Okay, it seems there is no question in the chat room. Well, I have a question for you and an advice. My question is that in your conclusion, you are claiming that your contribution is that the system you realized allowed you to communicate up to 2 meters, which is a considerable distance that has not been reached before. So let me say that this should depend on the error rate you have got at the receiver side. Well, you have never mentioned this in your work. So you see what I'm talking about? I mean, yeah, I mean this depends on the error that you will get at your receiver. You see, an advice for you is that you try to check the actual works on the coexistence of Wi-Fi and Li-Fi for the 5th generation, which is a hot topic right now. Well, this is all what I have to say for you. Thank you again, and we will go to the next presenter. Well, the next presenter will be Mr. Mohammed Mukti. His paper's title is Multi-Channel Access Control in the AE 802.11ad WiGig Networks Proposal and Analytical Analysis. The paper's ID is 190. I will give him the option to present his work. So please, Mr. Mohammed Mukti, accept my request.
Can you hear me?
Yes, I do hear you. I have sent you a request. Okay, great. Yeah, your presentation is displayed, so just go ahead and start to present your work.
Assalamu alaikum. Hello everyone, thank you for having me. My name is Mohammed Mukti. I am a PhD student and assistant professor at the University of BIM, and I'm going to be speaking to you today about my conference topic entitled Multi-Channel Access Control in the IEEE 802.11ad WiGig Network Proposal and Analytic Analysis. To do this, we opted for the following plan. We will start by presenting the evolution of Wi-Fi network. Then we will explore the future Wi-Fi generation, in which we will talk about the 802.11ad standard. In a second step, we will determine our research object and the reason that propelled us to take an interest in the new Wi-Fi generation. Then we will formulate our proposal to moderate and analyze its performance. We will end with a conclusion. So our first of bandwidth has become accessible just starting in 1997 with the birth of the first Wi-Fi standard, which offers a speed of 2 megabits per second. Then in 1998, the 802.11b standard came to offer a maximum theoretical rate of up to 11 megabits per second and operate in the 2.4 gigahertz frequency. In the same year, we saw the appearance of the 802.11a standard, which offers a speed of 54 megabits in the 5 gigahertz frequency band. Note that this frequency band is less sensitive to interference. In 2003, we also saw the arrival of the 802.11g standard, which brought the quality of service to Wi-Fi network. Then in 2009, the N standard was designed to achieve a speed of 600 megabits on the 2 frequency band 2.4 and 5 gigahertz. Finally, in 2012, two new Wi-Fi generations, the ID and the AES standard, were developed to achieve very high throughput, which is the range of gigabits. Several factors motivate the increase of Wi-Fi throughput, in particular the following use case. Allow the execution of application with high throughput consumption in the end service kiosk, sharing a very rich video stream like 4K, docking. The docking, for example, you can imagine a PC connected to these peripherals by Wi-Fi links, sharing 3D games, beyond the acronym of bring your own device. This paradigm describes allowing employees to use their personal equipment in the workplace. To meet this challenge, the Wi-Fi Gigabit Alliance Working Group proposed IEEE 8211ID, also called WGIG, to supply the gigabit worlds. The ID standard is developed used in a much higher spectrum of 16 gigahertz. It theoretically achieves maximum throughput of up to 7 gigahertz with the use of one channel, which is times higher than the throughput provided by the N standard. The 16 gigahertz band offers 4 separate channels of 60 gigahertz wide. We have seen that the standard offers 4 uncovered channels. So the using of this 4 channels simultaneously at the multi-channel MAC level can significantly improve network throughput compared to the single channel MAC protocol. Indeed, several concurrent transmission can take place in different disjoint channels simultaneously. Our proposal consists of simultaneously using the 4 channels in the access method to the MAC layer of the ID standard. This channel will be divided into a single channel reserved to control frames. The 3 remaining channels will be dedicated to data transmission. To show the operation principle of MAC method proposed for ID method is presented in this flowchart. The transmitting station select a 3 data channel and process to management channel to inform the receiving station of the selected data channel via an RTS packet using the CCSSP mechanism. If no channel fail, the transmission station will randomly wait for release of the data channel. The receiving station confirms the sending of data via each CTS packet sent in the management channel using the same CCSSP mechanism. We consider all 3 stations must be in the management channel. Both stations will switch to the selected channel to transmit the data. After receiving the data correctly, the receiving station must acknowledge receipt of the data to the transmitting station via an equipment message. So, to validate the proposed protocol, we used the analytical model of Bianchi and MATLAB to solve a nonlinear equation numerically generated by this model. The parameters used in the simulation are summarized in the following table. The duration of CFS, DFS, the value of equipment. At the beginning, we consider the impact of change in the number of channels compared to the number of stations in the system. This figure shows that the overall throughput of each station is improved each time we increase the number of channels. Increase the number of channels. Comparing the free curve, we also notice that the throughput decreases with the increase of the number of channels in the system. This increasing due to the larger number of collisions in the network. Sorry. Next, we estimate the effect of MPDU size in the performance of the proposed protocol and the single MAC protocol. The simulation result show that the system throughput increase with increasing MPDU size in both MAC protocol variation. Note also that this increase is considerably important in the proposed multi-channel MAC protocol. This is due to the number of wide channels available in the system. In conclusion, in this work, we are mainly interested in the AES standard, which use a new 60 gigahertz millimeter frequency band, which is the subject of our study. The critical study of AES standard led us to propose a new access approach to the MAC layer based on multi-channel access. To make a comparison with existing single-channel access method, we have represented different behavior related to performance evaluation based on Bianchi's model analytic. The result of this scenario have shown that our method in the MAC layer offers better performance, especially in terms of throughput. Thank you.
Well, thank you, Mr. Mohammed Mufti, for the presentation. So the floor has been open for any questions, and right now I'm checking the chat room for any questions. So it seems there is no question. So I will ask a question, or I just have a sort of.
Je pense, il y a une question. There is a question, huh?
In the chat room.
In chat room, yes.
What is it? I have no question here.
I have a question. So yeah, the guest.
He said I have a question. What's your question?
Quelle est la durée de RTS et CTS?
Okay.
Donc.
Yeah. Could you please answer this question?
Je n'ai pas mentionné en fait la durée de RTS et CTS.
Okay.
Donc CTS. En effet, je n'ai pas considéré la durée de RTS et CTS.
Okay.
Normalement, c'est la durée de... C'est l'adresse de destinataire plus l'adresse de destination. Mais c'est important.
Oui.
Mais
c'est important.
Oui. Je ne l'ai pas considéré. Oui, non.
Okay, you have to check this later.
C'est environ que c'est pas la même chose. Donc c'est tellement la vitesse la vitesse offerte, le débit offert par le standard AD est important d'ordre de 5 gigabits. Donc la de CTS et ATS est insignifiant.
Okay.
Contrairement à la norme B qui offre, je pense, 11 mégabits par seconde. 11 mégas par rapport à 7 gigas, c'est insignifiant.
Okay.
Thank you.
Well, I have
Yes.
could you please explain to us a little bit more on the analytical modeling where you have used the Bianchi model for those?
Ah, bien sûr. En fait, c'est un situation de Markov de deux dimensions. Donc, two dimension Markov chain. Donc, chaque étage, les étages verticaux représentent la décrémentation des étapes de back-off. Les étages verticaux, c'est les étapes de retransmission, les étapes après une collision, les étapes, c'est les étapes de horizontales représentent la décrémentation de back-off. Est-ce que c'est clair?
Oui, thanks again.
C'est un outil mathématique, il est utilisé donc pour la simulation de la norme 802.11. C'est le modèle le plus utilisé. Vous pouvez utiliser des simulateurs dédiés comme MS, OpNet, Omnet, des modèles mathématiques comme les chaînes de Markov, les réseaux de Petri, il y a un panoplie d'outils. D'accord.
Well, thank you again for your presentation and for your kind answers.
You're welcome. You're welcome.
Let's go to the next presenter.
Thank you.